Hey, welcome back. We're going to look at our third part. This is the mini class for this week, and it's about section 7, inverse functions. And I just want to point out that when you're reading, there are learning objectives at the beginning of each section. And you could use this as a checklist if you want to see, did you get what you should out of the reading? Can you check off all of these items once you're done reading it? So these are your goals when you're reading. But let's jump right in. So here's a function and its inverse. It's good to know this, that these are about converting degrees, temperatures in Fahrenheit to Celsius or Celsius to Fahrenheit. So these actually undo each other. And it's good to know that, let's see, what are these? Water boils at 212 degrees or 100 degrees. Water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. And your body is probably around 98.6 degrees Fahrenheit, which is 37 degrees Celsius. And then another two numbers to know, 61 and 16, those just reverse the digits. That's good to know. If it's 61 degrees or 16 degrees Celsius, it's going to be a little bit chilly inside. You should put on a sweater. And then the interesting thing is that at negative 40 degrees, if you spit into the air, your spit will freeze in the air and shatter when it hits the ground. That's what I've heard. I've never seen that done. The number is the same. Negative 40 degrees Fahrenheit is exactly the same as negative 40 degrees Celsius. And function 2 has them the other way. We'll input Celsius and we'll output Fahrenheit. So it's the same numbers but with the columns reversed. And as a graph, here's something interesting. If you plot it, this plot here, 212, 100, that's Fahrenheit to Celsius. And so this line is the line, that's function 1, and the other line is function 2. And notice that there's a symmetry. There's a symmetry around the line y equals x. X is the input, y is the output. And if you go up to these tables, you can see that the input of one function is the output of the other function, and same with the output and input. We just switched the input and output. And with formulas, these are the two formulas. Those actually undo each other. And I want to point out, so I don't have to come back to this, is that if we call this first one, function 1, y equals 5/9 of x minus 32, then the second function is going to be the same as x equals 9/5 of y plus 32. So they're actually the same formula, but with the input and output with x and y switched, and then for the second function you solve for y. That's something to remember. So let's go ahead. Let's get the actual definition of an inverse. If we have two functions, f and g, we say that g is an inverse function for f if g takes the output of f and gives you the input. So f takes the g takes the output of f and gives you back the inverse. And so we just have to check. So we want to verify, is g an inverse of f? What we're really asking is g composed with f the identity function? Is it the identity function? So is g composed with f of x equal question mark x? And let's just check that. So we need to simplify g of f of x, and we can do this from the inside out. Let's do that. So that's g of 5/9 times x minus 32 And if we use the formula for g that says just take whatever you have, multiply it by 9/5. So 9/5 times that input, x minus 32, and then to the result you add 32. That's the formula for g, and you can see that there's going to be some cancellation. The 5's cancel, the 9's cancel, and we're left with x minus 32 plus 32, and that sure enough equals x. So this is satisfied, and yes, g is an inverse for f. And actually, it's the inverse. We can write it the inverse, because if you have a function, then you only have one inverse, and you can use the definite article. So question, you should know by now, if you have a function f and its inverse, we write it like this, and it's not, that does not mean 1 over f. So there's a bit of clash in notation. F inverse means the inverse of f, not the reciprocal. So not reciprocal. So 3 questions you should be able to answer now. If not, go back. If you have a function and its inverse, how are the tables related? How are the graphs related geometrically? And how are the formulas related? There are 3 things to know that become very useful. Let's go to the next slide. Here's an example that is problematic, and what you should learn from this is that not every function has an inverse function, but we can salvage it sometimes. So here's the squaring function, and I can draw the error diagram. -2 goes to 4, -1 squared is 1, 0 squared is 0, so this is a 2 squared, 1 squared, 0 squared, so -2 squared, -1 squared. 1 squared is 1, and 2 squared is 4. If we try to form the inverse function, we should just take the input and output columns and switch them, and then we get this, that 4 unsquaring it, or the square root, should give you 2, but 4 also should give you -2. So right away we can see that it's not a function. And we can also look at the graphs. Here's the squaring function. It's this beautiful parabola, y equals x squared. But if we reflect it across the line y equals x by switching the x and y coordinate, we get a sideways parabola, but that does not satisfy the vertical line test. Here's a vertical line. It fails the vertical line test. So it's not a function. It's not a function, but we do need a function. We do want to have a square root function. The unsquare is not a function. So if we just get rid of the plus minus and have a function, we could just take the positive part, well, 0 and the positive part. That is a function, and the way to salvage it is to, we could change this, actually change it just slightly. Let's get rid of what I erased. We could change it, but we could change the domain restricted to x bigger than or equal to 0. So we want only positive numbers to go in. So if we take this part of the x squared curve and throw away the negative part, then we have a function who does have an inverse function, the square root. Sorry to make that complicated, but It's something to think about. The square root is always something problematic. We want it to be a function. We don't want numbers to have two square roots, even though there are two numbers that would square to give that number. Okay, so we should know that not every function has an inverse. We don't always get a function, and we need criteria. So let's go back to the definition of a function. The definition is that a function is actually a relation, but the condition is that each input value has just one output value. So if we take a relation, we can certainly change the domain and range. We can reverse the arrows, and we'll get a relation which is actually called the inverse relation. But that inverse relation is only a function if switching input to output, each output value corresponds to just one input value. So that's the condition. Each output value of the function should just correspond to just one input value. And if that's true about the function, we call it a one-to-one function. But that just means that you can reverse the input and output and still get a function. And sum it up like here, a function has an inverse exactly if it is one-to-one. That means a function has an inverse exactly if each output value corresponds to just one input value. And sometimes you have to change the domain, restrict the domain to make that happen. So one-to-one is also sometimes summed up with a horizontal line test. So 1-to-1 is really the horizontal line test. Every possible output, like here's the output of 2, y equals 2, this graph is good. There's only one input that gives that output right there. So this passes the horizontal line test, but y equals x squared, if you have y equals 2, well, there's actually a number down here about negative 1.4 and a number about over here, positive 1.4, that both have the same output. So that's not a one-to-one function. So the squaring function fails the horizontal line test. It's not one-to-one. Over here, you should recognize this is the inverse function 1 over x, and that actually does pass the horizontal line test, so it's one-to-one. And over here, this is the absolute value, sometimes written absolute value of x, or just with the vertical lines. Again, it fails the horizontal line test, so it's not a one-to-one function. It does not have an inverse function unless we restrict that domain. Okay, so let's verify that negative 2 times the absolute value of 2x minus 1 plus 2 does not have an inverse. Complicated example, but it's actually not hard to think about. Let's think about this in terms of what's really going on, graph transformation. There's a simple graph that we're starting with, and sometimes it's called the mother function, and that's y equals the absolute value of x. And then if I change it, let's say y equals the y equals 2x, absolute value of 2x, that's a horizontal stretching. So the graph here looks like absolute value. If you write y equals absolute value of 2x, you actually shrink horizontally. It'll be a steeper V shape. And then if you change x to x minus 1/2 and keep the 2 out there, I'm doing that to still have the absolute value of 2x minus 1. And this is a horizontal shift. And so the function now is shifted by 1/2 units to the right is going to look like a steep V shape, 1/2 there. And let's then multiply by -1, so negative absolute value of 2x minus 1. That's going to flip it vertically, and then we can multiply that by 2 to get -2 absolute value of 2x minus 1. That's going to be a vertical stretch. It's going to stretch it out vertically, and so we'll get the same vertex, but it'll be an even steeper V. And then finally, we want to add 2. Y equals -2, absolute value of 2x minus 1 plus 2. That's a vertical shift, and it's going to look exactly the same, but we're going to move that vertex up by 2 units up here, and it'll look like this. And I'm just pointing out that this complicated function is a result of a toolkit function and several graph transformations. It's like 1, 2, 3, 4, 5, 6, 7, or so on. But it starts out, it passes the horizontal line test. Each of these passed the horizontal line test, and so it's 1-to-1, 1-to-1. I know, actually, sorry, it fails the horizontal line test because there's some horizontal lines, many, that cross it 2 times. So it's not 1-to-1. So we can conclude it does not have an inverse. So that was really about transformations of functions. And let's verify that this does not have an inverse. This is a little bit simpler. Let me start with the mother function, the square root of x. You can see it's the square root of x. The next one is going to be square root of x minus 2. And the third one is going to be square root of x minus 2 minus 1. And what happens here, there's a horizontal shift. And over here, there's a vertical shift. And if we start with this function, let's draw all three functions, and I'll graph them in red. The square root function starts at the origin, and it goes like this. But if we shift it horizontally, now it's going to be shifted over by 2 units. It'll look like this. And now it's going to be shifted down by 1 unit. So this vertex is now 2, -1, and still looks the same. And this first one passes the horizontal line test. When you shift it, it still passes the horizontal line test. And when you shift it again, it still passes the horizontal line test. So they all pass the horizontal line test. They're all 1-to-1, and they all have inverses. And that's probably the best way to think about that complicated function. It starts with a simple function. Let's go to the next one. Just some facts. If g is the inverse of f, then we have this inverse notation, and it's not the reciprocal. It's not 1 over f of x, even though the negative inverse, -1 inverse, looks like that might be. It's just sort of bad notation. So it's not the reciprocal. And what this means is that take any x in the domain of f, take x, so x, plug it into the f function with f, and then plug it into the g function with g of f of x. You have to get back x. And it's also true that you could switch the functions. The first one we looked at f composed with g, but if you look at g composed with f, we also get f composed with g as x. those switched. So f is the inverse of g as well. And the domain of g is the range of f. The domain of f is the range of g. Those are switched. And there's that symmetry across the diagonal. That's something that you learned. And so here's steps to find the inverse of a function. First, you have to check that it actually does have an inverse. We want to take this formula, solve for x, interchange x and y, and then think a little bit more about the domain. So I think we have one example here. We're going to write this out as y equals root x minus 2 minus 1, and we're going to solve for x. So I'm going to, let's see, add 1 to both sides. And I'm going to square both sides. So y plus 1 squared equals x minus 2. And then I'm going to add 2 to both sides. So equals x. And now I'm going to switch x and y. And you can actually do these steps in either order. But we're going to end up with y equals x plus 1 squared plus 2. So f inverse of x is x plus 1 squared plus 2. But we have to think about the domain. And that means we need to figure out the range here. The range here is that x must be bigger than or equal to 2. So that means that root x minus 2 is going to be bigger than or equal to 0. And root x minus 2 minus 1 is going to be bigger than or equal to negative 1. And so the range here is y is bigger than or equal to negative 1. And that means that the domain over here, the domain, x has to be bigger than or equal to negative 1. And it would help to see a picture of this. I'll just draw a picture. I'm going to get that diagonal. And let's do the first one in green. I think we saw that the vertex was here at 2, negative 1. And it looked like this. So the inverse that we just found passes through negative 1, 2. That's the vertex because we switch x and y. And it's going to be right up here. And the part that we had to get rid of was the other part of this parabola, because that's the reflection of this part. And if we included that yellow part for the original function, it would not be a function. So we have a formula for the function, but we do have to restrict the domain. The domain is only numbers from negative 1 all the way up to infinity. So we can write that negative 1 to infinity. And let's move on. And I think I'm done. Yeah, we're done with this. So let's stop here, and I'll see you back in class.